You know, when you walk into a building and you feel that cool, comfortable air, have you ever stopped to think about how it all actually comes together? Well, it all starts with a single line on a drawing. Today, we're going to trace that line's complete journey, from a simple blueprint all the way to a fully functioning CLIMAVER HVAC system. We'll be diving into the whole engineering process, seeing how an idea becomes reality on a real-world construction site, following the kinds of strict standards you'd see from places like Aramco and ASHRAE.
So that's really the big question, isn't it? How does a flat, two-dimensional line on a screen actually turn into the thing that makes a building comfortable? You know, its breathing lungs. That's exactly what we're going to break down today. We're going to follow the trail of critical decisions and the nitty-gritty calculations that make it all happen.
All right, so first things first. Everything, and I mean everything, starts with the 2D HVAC plan. Now, don't think of this as just a rough sketch. No way. This is the project's Bible, the single source of truth. It lays out the entire game plan, the complete design intent, long before anyone even touches a calculator.
And a really solid plan, man, it's packed with information. You've got all the big players right there. The chiller, the air handling unit, the piping. It tells you exactly how much air needs to move, that's the CFM, and it maps out the highways for that air, the ducts showing their sizes and where they're going to run. It even pinpoints where every single diffuser and grill will go. And super important, it includes little notes, key limitations, like mentioning this is a low-pressure system, which is perfect for CLIMAVER. Getting this right from the start, well, it sets the stage for the entire project.
Okay, so we've got our map, our blueprint. Now it's time to switch gears from pictures to physics. This is where the real engineering kicks in. We're about to translate all that visual information, that design intent, into cold, hard numbers that will define how this system actually performs. So the very first number we absolutely need to nail down is the airflow. It all starts at figuring out the building's cooling load, which we measure in something called tons of refrigeration, or TR. Now, a really common rule of thumb in the industry for standard comfort cooling is a simple relationship. You take the TR value and multiply it by 400. So let's say we're working with a 30-ton system. We just do the math. 30 times 400 gives us our magic number, 12,000 cubic feet per minute, or CFM. That's our target.
But, and this is a huge but, you gotta be careful here. This is a classic rookie mistake and a massive red flag for any consultant reviewing your work. You can't just blindly throw that times 400 rule at every project. You have to be able to justify it. Does it align with the energy goals? What about fresh air requirements? Without that solid reasoning, your design is going to get stamped, rejected, faster than you can say CFM.
All right, next up is the water. We need to figure out the chilled water flow rate because that's what's actually carrying the cooling power around. And this is where, as an engineer, you kind of have to speak two languages. Especially on big projects, say in Saudi Arabia, you'll be expected to provide calculations in both imperial units, that's gallons per minute, or GPM, and in SI units, liters per second. Using our same 30-ton system, that works out to 72 GPM, which is the same as 5.04 liters per second. You need both of these numbers to get your pipes and pumps sized just right.
Okay, so quick recap. We know how much air we need to move, and we know how much water we need to move. So what's next? Well, we need to build the highways for all that air to travel on. We're talking about the ducts. And this next step is absolutely crucial, getting the size of those pathways perfect. Now, with a system like CLIMAVER, which is designed for low-pressure applications, two things are king: noise and efficiency. You don't want a system that sounds like a jet engine, right? So we turn to the industry standards, like ASHRAE and SMACNA, and they give us these recommended speed limits for the air. The idea is simple. You want the air moving faster in the big main ducts, kind of like a freeway, and then you want it to slow way down as it branches out and gets closer to you in the room. Sticking to these numbers is the secret to a system that's quiet, comfortable, and doesn't waste energy. Okay, lean in for this one, because we're about to talk about what is probably the single most common and easiest mistake to make when you're designing with CLIMAVER. It's what I call the critical correction. It's all about accounting for the thickness of the panels themselves. It sounds like a tiny detail, but trust me, forgetting it can wreck your entire calculation.
Let's just look at the numbers to see what I mean. So, your initial math might say you need a duct that's 1,000 by 800 millimeters on the outside. You run the calculation, and it gives you an air velocity of around 7 meters per second. Looks good, right? You're within the limits, but, and here's the catch, CLIMAVER panels are 25 millimeters thick. That means the inside space, the actual area the air has to move through, is smaller. When you redo the math with that smaller internal area, guess what? The actual velocity of the air jumps up to almost 8 meters per second. All of a sudden, you're dangerously close to breaking your own design rules.
So the takeaway here is pretty simple.
Ignoring this little correction is an instant red flag in any design review. It's one of those details that immediately separates the pros from the amateurs. Making that correction shows the consultant, hey, this person actually knows the material they're specifying. It's the difference between getting your design approved and getting it sent right back to your desk.
All right, our numbers are solid, they've been double-checked. Now we get to leave the flat world of 2D drawings behind and step into the world of virtual construction. This is the cool part. We're going to build the entire system in a 3D computer model before a single piece of duct is ever cut.
Honestly, in today's world, this 3D modeling or BIM coordination isn't optional, it's essential. Think of it like a test drive for the building. It lets us see everything before it's real. We can check if our ducts are going to crash into some plumbing. We can make sure there's actually enough space for someone to get in and do maintenance later. And, big one here, we can confirm that the whole thing is actually buildable in the real world. Finding a problem here saves a mind-blowing amount of time, money, and headaches on the actual job site.
And now we get to the moment of truth, the final phase. This is where all the planning, all the calculations, all the virtual modeling, this is where it all gets real. We're taking that perfect digital model and turning it into a physical system out on the construction site. When it comes to execution, the name of the game is quality control. There are no shortcuts here. It's a whole series of checkpoints. First, you get the actual materials approved. Then, you inspect those materials when they arrive on site to make sure they're what you ordered. You check the dimensions of every piece of ductwork as it's built. And critically, you get the consultant to come and inspect everything before it gets covered up by a ceiling. It's this step-by-step process that guarantees the thing you built is the thing you designed.
And that really brings us to the most important point of this whole explainer. Every single number we talked about, that CFM calculation, the duct dimensions down to the millimeter, the velocity checks, none of it is just theory in a textbook. Every number has a real, direct, and powerful impact on what happens out on that site. It affects everything from what materials get ordered to how well the system actually works in the end.
So I want to leave you with this question. The next time you're looking at a set of plans, ask yourself this. Is this just a pretty drawing, or is it a buildable reality? Because at the end of the day, the gap between those two things, that's where successful engineering lives. It's our job to bridge that gap and make sure our designs aren't just ideas, they're built for success.